What if I told you that one of the most important discoveries about chaos began with a mistake? Not a careless mistake, not a simple arithmetic error, a conceptual mistake made while trying to solve one of the hardest problems in physics. In the late 19th century, mathematician Henri Poincaré was studying a deceptively simple question. If three objects are moving through space and pulling on each other with gravity, can we predict exactly what they will do? At first, the problem seemed like something mathematics should eventually conquer. After all, Isaac Newton had already given the world equations that described gravity with astonishing precision. The planets followed predictable orbits. The moon followed predictable patterns. If the laws were known, surely the future should be calculable. But then Poincaré discovered something disturbing. The equations were deterministic, meaning the rules were fixed. Yet the long-term behavior could become incredibly difficult to predict. Tiny differences in the starting conditions could grow into enormous differences later. And hidden inside that realization was the mathematical seed of something we now call chaos theory. But here's the twist. Poincaré didn't begin by trying to discover chaos. He was actually trying to understand whether the solar system was stable. And when he made a mistake in his original analysis, correcting that mistake forced him to confront a much stranger reality. A reality where trajectories could twist, fold, and become so tangled that long-term prediction could break down. That discovery would help reshape mathematics, physics, astronomy, and eventually even the way we think about uncertainty itself. But chaos was only one piece of Poincaré's extraordinary story. He helped create modern topology. He transformed the study of dynamical systems. He contributed to mathematical physics, probability, celestial mechanics, and the philosophy of science. And he played an important role in the intellectual road that led to Einstein's theory of relativity. So how did one man manage to reach into so many different areas of science? And why are mathematicians, physicists, and computer scientists still using ideas associated with him more than a century after his death? The story begins in 19th century France, with a child whose mind seemed to work differently from everyone around him. Henri Poincaré was born on April 29, 1854, in Nancy, France, in the Lorraine region. His father, Léon Poincaré, was a respected physician and professor of medicine. His mother, Eugénie Uzhine, came from an educated family, and she played an important role in Henri's early development. The Poincaré family lived in an intellectually rich environment. Medicine, science, mathematics, and education were part of everyday life. And Henri was an unusual child. He was physically awkward and struggled with poor eyesight. During childhood, he also suffered from a serious case of diphtheria. But while his body sometimes seemed to work against him, his mind was developing at extraordinary speed. At school, his abilities became impossible to ignore. He attended the Lycée in Nancy, where he excelled in mathematics and other subjects. His teachers quickly recognized that they were dealing with a remarkable student. But Poincaré's talent wasn't simply about calculating faster than everyone else. He had something more unusual, an extraordinary ability to see relationships between ideas. He could take a difficult mathematical concept, hold it in his mind, and mentally manipulate it as though it were a physical object. His poor eyesight may even have contributed to this habit. Because he sometimes struggled to see what lecturers were writing on a blackboard, he learned to rely heavily on listening and mental visualization. He absorbed ideas through words, then rebuilt them inside his own mind. That way of thinking would become one of the defining characteristics of his career. Poincaré didn't see mathematics as a pile of formulas. He saw it as a landscape. Different problems could be connected. A technique from one field could suddenly unlock another. A physical problem could inspire a mathematical idea, and that mathematical idea could later transform physics. That instinct to connect things that other people treated as separate would become his superpower. In 1873, Poincaré entered the École Polytechnique in Paris, one of France's most prestigious scientific schools. Mathematics quickly became his strongest subject. Physical activities were much harder. His coordination was poor, and he wasn't naturally athletic. But intellectual challenges seemed to have the opposite effect on him. They energized him. After the École Polytechnique, he studied at the École des Mines École des Mines, where he trained as a mining engineer. For a time, Poincaré actually worked as an engineer. He visited mines. He studied industrial problems. He worked with real physical systems. And this experience mattered, because Poincaré never believed mathematics belonged in a sealed-off ivory tower. For him, mathematics was a way of understanding reality. While working as an engineer, he continued his mathematical research, and in 1879, he earned his doctorate in mathematics from the University of Paris. His doctoral work focused on differential equations, equations that describe how things change. And even at this early stage, Poincaré was already thinking differently. His work was brilliant, but parts of it were difficult to follow. That pattern would continue throughout his career. Poincaré could see ideas very quickly, sometimes faster than he could explain them. He would often leap toward the deep structure of a problem, leaving other people to reconstruct the path he had taken. Soon, he began teaching mathematics at the University of Cannes. Within a few years, his reputation exploded. By 1881, he had moved to Paris. And now, he was entering the problem that would change everything. Imagine the Earth traveling around the Sun. The Sun pulls on Earth through gravity, while Earth pulls back on the Sun. Simple enough. Now add the Moon. Suddenly, the situation becomes more complicated. The Sun pulls on the Moon. The Earth pulls on the Moon. The Moon pulls on Earth. Every object affects every other object, and every change in motion creates another change. Now imagine trying to calculate the exact positions of all three objects, not just tomorrow, but thousands or millions of years into the future. That's the three-body problem, and it had been troubling mathematicians for generations. The basic laws were known, the equations were known, but solving the system in a simple, exact, universal way was another matter entirely. Poincaré became fascinated by it, and in 1887, King Oscar II of Sweden and Norway announced a major mathematical competition connected to celestial mechanics. The challenge asked mathematicians to investigate the stability of the solar system. Could mathematics prove that the planets would remain in stable orbits? Poincaré attacked the problem, and his work was so impressive that he won the competition. It looked like a triumph, but then something went wrong. As the manuscript was being prepared for publication, mathematician Lars Fragmen noticed a serious issue in the argument. Poincaré went back over the work, and he realized that the criticism was valid. His original analysis had contained a conceptual error in the way he was treating the behavior of the system. He had been working toward a picture of stability, but the corrected mathematics revealed something far more complicated. The problem wasn't simply that the calculation was difficult. The underlying system itself could contain incredibly intricate behavior. And this is where the story becomes extraordinary. When Poincaré corrected the error, he began studying the geometry of possible trajectories. Instead of asking only, where will this planet be at this exact moment? He began asking a deeper question. What does the entire system look like when we consider all possible motions? That change in perspective opened a completely new mathematical world. Imagine releasing three objects into space. Each one is pulling on the others. At the beginning, you might start with two situations that are almost identical. In one, an object begins here. In the other, it begins just slightly over there, perhaps by an incredibly tiny amount. You might expect the two systems to remain almost identical. But in a sufficiently complicated dynamical system, they can gradually separate. The difference grows, and grows, and grows. Eventually, the two systems can look completely different. This is called sensitive dependence on initial conditions, and it is one of the defining features of chaotic behavior. Here's the important part. Chaos does not mean randomness. A chaotic system can follow perfectly precise laws. There may be no randomness in the equations at all. The problem is that tiny uncertainties in the starting conditions can grow so dramatically that long-term prediction becomes practically impossible. Think about weather. The atmosphere follows physical laws. There is no magical force deciding what tomorrow's weather should be. But the atmosphere contains countless interacting variables: temperature, pressure, humidity, wind, radiation, and more. A tiny measurement error today can become a major difference days later. Poincaré saw the mathematical foundations of this kind of behavior decades before the modern language of chaos theory became popular. And his discovery came from a problem that seemed almost completely unrelated to everyday life: the motion of planets. Poincaré discovered structures called homoclinic points and homoclinic tangles, complicated intersections between trajectories in a dynamical system. The geometry could become unbelievably intricate. Trajectories could weave around each other in ways that made the system's future extraordinarily difficult to track. It was one of the earliest mathematical glimpses of chaos, and it changed the direction of dynamical systems forever. But Poincaré wasn't finished. In fact, he was about to attack a completely different question. What does it actually mean to understand the shape of something? Forget planets for a moment.
Imagine a café mug.
Now imagine a donut. They look completely different. But suppose you could stretch and deform the mug without tearing it or gluing anything together. You could gradually transform the mug into a donut. From the perspective of topology, they have something important in common. They both have one hole. Topology studies properties that survive continuous deformation. It isn't primarily concerned with exact distances or angles. It asks deeper structural questions. How many holes does an object have? Is it connected? Can one shape be transformed into another without tearing? What happens to loops drawn on its surface? These questions might sound abstract, but they became one of the foundations of modern mathematics. And Poincaré was one of the people who built that foundation. In the 1890s, he developed powerful new ideas about spaces, surfaces, and the behavior of loops. One of his most important concepts was the fundamental group. The intuition is surprisingly simple. Imagine drawing a loop on a surface. Can you shrink that loop down to a single point without leaving the surface? On a sphere, a loop can generally be shrunk. But on a donut, imagine drawing a loop around the central hole. You can't shrink that loop to nothing without breaking the loop or passing it through the hole. The behavior of loops tells us something about the underlying shape. Poincaré developed algebraic tools that could capture this information. And then he asked a question that would haunt mathematics for nearly a century. Could you identify a three-dimensional sphere by looking at how loops behave inside the space? In 1904, he formulated what became known as the Poincaré Conjecture. In simplified terms, it proposed that a certain type of three-dimensional space with no essential holes must be equivalent, in the topological sense, to a three-dimensional sphere. The statement was deceptively simple. The proof was anything but. For decades, mathematicians tried to solve it. They developed new techniques. They created new mathematical machinery. Entire areas of geometry and topology grew around problems connected to the conjecture. And still, the problem survived. Then, almost a century later, a Russian mathematician named Grigory Perelman changed everything. In 2002 and 2003, Perelman published a series of papers using ideas based on Ricci flow, building on earlier work by Richard Hamilton. His work ultimately established the Poincaré conjecture. Poincaré had been dead for 90 years, but the question he had posed was still powerful enough to drive mathematics forward. That's one of the strangest things about mathematical discovery. A scientist can disappear. The question can remain. And sometimes the question becomes more influential than the person who asked it. But topology was only one part of Poincaré's mathematical revolution. He also transformed the study of differential equations and dynamical systems. A differential equation describes change. It can describe the movement of a planet, the flow of heat, the oscillation of a machine, or the growth of a population. Traditionally, mathematicians often tried to find an exact formula for the solution. Poincaré realized that sometimes you don't need the formula. You can understand the behavior of the system by studying its structure. Imagine every possible state of a system as a point. As time passes, that point moves. Now imagine all possible starting points. Together, their paths create a geometric picture. Poincaré developed ways to study those pictures. He could identify stable regions, repeating behavior, cycles, and complicated trajectories. This was a major shift in mathematical thinking. You don't always have to calculate the exact future. Sometimes you can understand the shape of all possible futures. That idea became central to modern dynamical systems. Today, similar methods appear in physics, engineering, biology, climate science, robotics, and many other fields. And once again, Poincaré had found a way to turn an impossible-looking calculation into a question about structure. But then came another revolution. Physics itself was changing. At the beginning of the 20th century, scientists were struggling with a deep conflict between classical mechanics and electromagnetism. Maxwell's equations suggested that light travels at a fixed speed. But classical mechanics treated space and time differently. Physicists such as Lorentz, Lorentz developed mathematical transformations that helped reconcile electromagnetic theory with observations. Poincaré studied Lorentz's work deeply. In 1905, he published important research on Lorentz transformations, the principle of relativity, and the mathematical structure connecting space and time. That same year, Albert Einstein published his famous paper on what became known as special relativity. This is where the historical story is often oversimplified. It is tempting to ask, who discovered relativity first? But that question can create a misleading picture. Poincaré and Einstein approached the problem from different angles. Poincaré worked extensively with the mathematical structure of Lorentz transformations and the symmetry of physical laws. Einstein approached the problem from a more physical and conceptual perspective, especially focusing on the relativity of simultaneity and what the laws of physics mean for observers moving relative to one another. Their work overlapped in important ways. But they were not simply making the same argument, and the history should not be reduced to a story about one man stealing an idea from another. Scientific breakthroughs rarely happen in isolation. They emerge from conversations between theories, experiments, mathematics, and researchers working across years and decades. Lorentz mattered, Poincaré mattered, Einstein mattered, and so did many others. Poincaré's work was an important part of the transition from classical physics toward modern ideas about space, time, and relativity. But perhaps even more fascinating was his interest in what science itself means. Poincaré wasn't satisfied with discovering equations. He wanted to understand how humans discover them. He asked questions about mathematical truth, scientific conventions, physical reality, and the limits of knowledge. He became one of the most influential philosophers of science of his generation. One idea associated with him is especially memorable.
Logique proves.
Intuition discovers. For Poincaré, mathematical creativity was not simply a mechanical process. You could work on a problem consciously for hours, days, even weeks, and then, unexpectedly, the answer could appear. A connection suddenly becomes visible. Pattern snaps into focus. Poincaré described experiences like this in his own writing. One famous episode occurred while he was working on automorphic functions. He had struggled with the problem for some time. Then, while stepping onto a bus, an idea suddenly appeared. The connection seemed to arrive from nowhere. But Poincaré didn't believe the mind had performed magic. He believed that conscious effort and unconscious mental work were interacting. The conscious mind prepares the problem. The unconscious mind continues processing possibilities. And then, sometimes a useful combination suddenly reaches awareness. The insight is only the beginning. Afterward comes the hard work of checking it, proving it, and turning it into mathematics. That description of creativity sounds surprisingly modern. And it tells us something important about Poincaré himself. He wasn't a machine for producing equations. He was fascinated by the human mind that produced them. His personality was also more complicated than the myth of the flawless genius suggests. He was extraordinarily productive. He was deeply curious. He could move rapidly from one subject to another. But he also made mistakes. Some of his mathematical writing was difficult to follow. He could pursue several ideas at once. And sometimes his intuition moved faster than his explanations. That isn't a weakness unique to Poincaré. It's a reminder that extraordinary intelligence does not mean perfection. The famous error in his three-body work makes that especially clear. His mistake didn't make him less brilliant. In some ways, it shows why he was brilliant. He recognized the error, corrected it, and then followed the unexpected consequences. Instead of defending his original conclusion, he allowed the mathematics to change his mind. That's an essential part of science. The willingness to discover that nature is stranger than your first idea. Poincaré also had a quieter personal life than his scientific reputation might suggest. He married Louise Pauline d'Andecy Eloise Poulain d'Andecy, and they had 4 children. He remained deeply involved in French academic and scientific institutions. He was elected to the French Academy of Sciences in 1887. He later became its president. In 1908, he was elected to the Académie Française, received international recognition as well, including election as a Fellow of the Royal Society. By this point, Poincaré had become one of the most famous intellectuals in Europe. But he wasn't interested only in impressing other scientists. He wanted ordinary educated readers to think about science. He wrote books such as Science and Hypothesis, The Value of Science and Method. These works explored questions that remain relevant today. What makes a scientific theory useful? How do scientists choose between competing descriptions? Where does mathematical certainty end? How much of scientific knowledge depends on conventions? And how does creative insight actually happen? Poincaré's philosophy became known in part for its emphasis on conventionalism. But conventionalism does not mean that science is simply made up. Nature still imposes constraints. Experiments still matter. Observations still matter. But sometimes, several mathematical descriptions can represent the same physical relationships. Scientists may choose the description that is simplest, most convenient, or most useful. For Poincaré, understanding science meant understanding both the external world and the human systems we use to describe it. And that idea connects directly back to his mathematics. Again and again, he looked beneath the surface. A planet's orbit was not just a line in space. It was part of a dynamical system. A shape was not just a collection of points. It had deeper topological properties. An equation was not just a formula. It represented a family of possible behaviors. A scientific theory was not just a collection of facts. It was a framework for organizing experience. This way of thinking made Poincaré extraordinarily influential, and his influence only grew after his death. In the 1960s, meteorologist Edward Lorentz was working with computer models of the atmosphere. He discovered that tiny differences in initial conditions could produce radically different long-term predictions. The result became famous as the butterfly effect. The popular image is that a butterfly flapping its wings could eventually cause a hurricane. That's a dramatic metaphor, but the deeper idea is more precise. In a chaotic system, 2 states that begin extremely close together can eventually diverge dramatically. The atmosphere is one example, and Poincaré had already uncovered the mathematical foundations of this kind of sensitivity decades earlier. His work helped prepare the intellectual ground for chaos theory. Today, chaos appears in studies of weather, turbulence, ecosystems, fluid dynamics, celestial mechanics, biological rhythms, and countless other systems. And the strange thing is this: chaos doesn't tell us that the universe is unpredictable because the universe is random. It tells us that prediction itself can have mathematical limits. Even when the rules are exact, even when the equations are deterministic, even when the system contains no randomness at all. That is one of Poincaré's deepest legacies. But there is another. His mathematics continues to influence space exploration. Modern spacecraft navigate through complicated gravitational environments. Engineers study stable and unstable trajectories. They search for efficient paths through the solar system. They analyze how tiny changes in velocity can alter a spacecraft's future. The computers are vastly more powerful than anything Poincaré could have imagined. But the questions are surprisingly familiar. How does motion evolve? Where are the stable paths? Where are the unstable ones? What happens when several gravitational influences interact? Poincaré's ideas about dynamical systems remain part of the conceptual toolkit. His topological ideas have also spread far beyond pure mathematics. Topology now appears in physics, condensed matter, quantum systems, robotics, data analysis, geometry, and network science. Scientists use topological ideas to identify structural features that can remain meaningful even when systems change continuously. And once again, the central theme is structure. Look past the surface. Find what survives. Find what matters. Find the hidden organization beneath apparent complexity. Poincaré died on July 17, 1912, in Paris. He was 58 years old. His death came unexpectedly after an operation, and the reported cause was an embolism of the heart. He left behind his wife, 4 children, and an enormous scientific legacy. But perhaps the most remarkable thing about his legacy is how many different disciplines still carry his name. Poincaré maps, Poincaré sections, Poincaré recurrence, Poincaré duality, the Poincaré conjecture. These are not just historical labels. They represent ideas that remain active in modern mathematics and science. And then there is the strangest part. Poincaré's work often began with questions that looked simple. Can the planets remain stable? Can we classify a shape? Can we understand the solutions of an equation? Can we reconcile mathematics with physical reality? But underneath each question was something much deeper. How can simple rules create complicated behavior? How can we understand something without calculating every detail? How much of reality can mathematics capture? And where does human intuition fit into the process? Those questions have not disappeared. They have become more important. We now live in a world dominated by complex systems, weather systems, global networks, biological systems, artificial intelligence, financial markets, spacecraft, social networks. Each one contains enormous numbers of interacting components. And sometimes, tiny changes can produce enormous consequences. Poincaré's work teaches us that complexity doesn't necessarily mean there are no rules. Sometimes the rules are incredibly simple. The complexity comes from the interaction. That may be why his work feels so modern. He understood something that many people still find counterintuitive. Knowing the laws does not always mean knowing the future. And discovering that limitation is not a defeat. It is a discovery. Poincaré did not simply give science more equations. He gave scientists new ways to think. He showed that when an exact solution seems impossible, you can study the geometry of the possibilities. When a system seems unpredictable, you can search for structure inside the chaos. When two subjects seem unrelated, you can look for the hidden connection. And when your own theory turns out to be wrong, you can follow the mistake. Because sometimes the mistake is pointing toward the discovery. More than a century later, Henri Poincaré's questions are still alive. The planets still move. The atmosphere still changes. Complex systems still surprise us. Mathematicians still study spaces and shapes that Poincaré helped teach us how to see. And scientists still confront the same fundamental problem he encountered while studying 3 bodies in motion. How can a universe governed by precise laws produce behavior that is so difficult to predict? Maybe the most important lesson is not that Poincaré understood everything. He didn't. It's that he understood how to keep looking when the easy answer failed. And perhaps that's where his story becomes personal. Because every one of us lives inside a system far more complicated than we can fully calculate. Our decisions interact with other people's decisions. Small choices accumulate. Tiny changes can redirect entire lives. We rarely know exactly where the trajectory will lead. But that doesn't mean there is no structure. It means the structure may be deeper than we can see. And that leaves us with a question Poincaré would probably have appreciated. If the universe can hide extraordinary complexity inside simple rules, what other patterns are already surrounding us, waiting for someone curious enough to notice them?